Say you are walking through the forest. It's getting late and the light is waning. You see something further down the trail, but you're not sure what it is. Your heart begins to race a little. The closer you get, the more details you can see. Suddenly you realize it's just a rock. You breathe a sigh of relief. What just happened? Your brain was making a statistical guess from limited information. Humans are hardwired to look for patterns. We have a bias towards seeing things that aren't really there. This is a survival mechanism. If a predator had been hiding behind that tree, you would have been ready. But this bias means that we have to be very careful, especially with visual information, because we can easily be fooled. This is why understanding statistics, how data are collected, interpreted, and visually presented, is very important. Our modern-day forest is made up of information, non-stop information. News stories, reports from politicians and interest groups, rumors, and hearsay. It all flows instantaneously to us via our smartphones, tablets, and computer screens. Much of this information is spread visually using charts, graphs, tables, infographics, and memes. Just like our primitive ancestors, we may see things that aren't really there in the forest of information. People often think of numbers as pure truth. 2 + 2 always equals 4. But numbers, especially statistical ones, can lie. One reason statistical numbers can lie is that they are, by their very nature, incomplete. To create a statistic, you need to collect data. Most of the time, we're limited in how much data we can get. We can usually only take a sample. Data are a sample taken from a whole population. Because data are just a sample of something bigger, it means there is a chance for bias. Say you are a fruit picker in a cherry orchard. Your job is to pick only the ripest, biggest, and most perfect cherries. You leave all the blemished, rotting, and small cherries on the tree. You could hand your basket of picked fruit to someone and tell them all the cherries in the orchard are just as perfect as these. But your sample wasn't random. You've only picked the best ones. So it isn't an accurate representation of all the orchard's cherries. Data that are cherry-picked is one kind of bias commonly seen in statistics. Cherry-picked data are often associated with something called confirmation bias. This is the tendency for people to only pay attention to things that reinforce their beliefs. For instance, say your politically active friend shares an infographic with you about a shocking new study. Rats were given genetically modified corn and subsequently grew huge, horrifying tumors. Being naturally skeptical, you decide to look at the actual study. You find that the study used very few rats, and the breed was prone to developing spontaneous tumors. Looking further, you find that an interest group opposed to genetically modified foods paid for the study. Looks like this could be an instance of confirmation bias. Data usually start out in table form. Can you tell by looking at this table what the most popular baby name is? Probably not. In order to make sense of this information, we need to put the data into a form that our brains can process visually. Depending on the type of data, there are a few different ways to do this. One of the most versatile is a bar chart. Bar charts are a way of sorting information into separate categories. Once the data are arranged, we can easily compare the categories and spot trends at a glance. The highest bar in a bar chart is called the mode. Numerical data can be visually arranged in a few different ways. One way is to make a histogram. A common histogram shape is the bell curve. The bell curve shape appears when plotting everything from milk production to shoe size. The bell curve is often called the normal distribution. If you've ever watched The Price is Right, you've probably seen a game called Plinko. In Plinko, a contestant drops pucks down a board with rows of pins. The puck bounces around randomly before falling into a category at the bottom. What people may not realize is that the basic idea for Plinko dates back to 1889 with the invention of the Galton box. Amazingly, this device produces a real-life bell curve. Balls get bumped around, but mostly end up somewhere in the middle. There are only a few paths a ball can take to get to the edges, but lots of paths to get to the middle. We are often interested in knowing the middle or central value for a set of data. A familiar measure of central value is the average, also called the mean. The mean is right in the middle when your histogram is perfectly symmetrical. But when you have outliers, the mean can give you a distorted picture of what the average value is. For example, say you wanted to know the average annual income in a small town. Most people in the town make around $40,000 a year. But there is one celebrity in town that makes $4 million. Her huge salary is an outlier on the curve, but dramatically shifts the mean. Fortunately, there is another measure that works better in situations like this, called the median. If you organize your numbers in order of smallest to largest, the median is the middle number. When you've got weird outliers, the median is a better way to get a more accurate central value. An often used trick is to report mean or median depending on which number will cast the most flattering light. When you hear something is an average, it doesn't tell you much unless you know what kind of average it is. Mean, median, or mode. Because life is full of irregularities, most distributions won't be perfectly bell-shaped. That's why it's helpful to know a little something about how much the data deviate from the mean. Luckily, the standard deviation can do just that. When the values are all snugly clustered around the mean, the curve is steep and narrow, and the standard deviation is small. When the values are spread out and the curve is flatter, the standard deviation is large. The standard deviation can give you an idea of how much weight to give a statistical relationship. Say a study showed that eating pickles results in weight loss. But the study has a large standard deviation. Therefore, these claims could be a bit dubious. You may have encountered the phrase, correlation does not imply causation. For instance, rain and clouds are statistically correlated. But from statistics alone, we don't know if rain causes clouds or if clouds cause rain. Statistics only tell us there is a correlation. We need more science to establish causation. Statistics can never prove causation. While you can use various mathematical tools to grade a correlation as weak or strong, all you're ever going to get is correlation. On the other hand, statistical correlations can be a powerful and informative tool. Take lung cancer, for example. At the turn of the century, lung cancer was extremely rare. But by the mid-1980s, lung cancer had become the leading cause of cancer deaths worldwide. What had changed? In short, the introduction of the manufactured cigarette. The Tobacco Institute, a lobbying group for the tobacco industry, was founded in the 1950s to cast doubt on the theory that cigarette smoking caused lung cancer. Their strategy was to repeatedly apply the correlation does not imply causation argument. If a person gets lung cancer, it is impossible to prove that tobacco smoke was the cause. The tobacco lobbyists capitalized on this limitation. However, over time, the statistical link became undeniable, culminating in 1998 with the largest civil settlement in U.S. history. The 4 largest cigarette manufacturers agreed to pay $206 billion to 46 states. Part of the deal was to dissolve 3 lobbying groups, including the Tobacco Institute. That is the power of statistics.